Hi, so we're going to be using a human, me, to like try and solve linear transforms. And because we're trying to gain intuition into like generalization of neural nets, and it seems to be like when a neural net trains on a training set, like it's moving all of the input points, in a particular way. And so, like we're trying to see like if you can gain intuition in like the two-dimensional case, if that would help you in like the general case. And so like it probably wouldn't, but like we're going to like do that anyway. So yeah, I mean like the visualization is just a single layer, or like a zero layer, depending on how you count layers. It just has one output layer, and that's it. And everything is two-dimensional. And the training set is the colored lines. So it's trying to move these squares, and like the squares are very small, so they're hard to see. But it's trying to move the red square over to the red circle, and the green square over to the green circle, and the blue square over to the blue circle. And this one looks like it's kind of hard, so I'm actually going to like just do a different training set. And I don't see where the green one is on this. Okay, there it is. Okay, so yeah, but like I can't see it, so I need, okay. All right, here we go. All right, so we're like a human, and we're gonna try to like like solve these training sets, or like like fit them manually. So like these are the weights, right? So there's like 6 weights. Like you saw when it was the optimizer, like we're using Atom, it also updates the weights. And there's 6 weights, 2 biases, including 2 biases, and biases. And okay, so we're just gonna like get into it. Like I don't know how this is going to work. I mean, like I'm probably not gonna be able to do it, but so yeah, okay, so like looking at this one, okay, so like the green square wants to go down, and this red square wants to go up. So I'm thinking flipping along or over the horizontal axis, right? So like we want to affect the y dimension, and we want to flip it over. Beautiful. Beautiful, okay. Then we want to move the red guy over, but like it has to move more than the other guys, so I don't know how to do that. So yeah, we'll just yeah, okay, see, so I'm not gonna know how to like move, right, because this red thing has to move more than like the green thing. And maybe if we like do a horizontal shearing, but that's not, yeah, that's not gonna, okay, so we'll now see what like Atom Optimizer does in this case. Some of my problem is that it's probably going to go like too quickly to notice, so I might have to like slow. How would I slow that down? I don't know, but anyway, okay, so let's just look at the Atom Optimizer. Okay, whoa, how did it do that? Yeah, like it moves way too quickly. So well, let's just let it finish, I guess. Yeah, like it's doing all sorts of crazy stuff. Like I'm not sure as a human we're going to be able to comprehend this. This is high level stuff. This is high-level gradient descending. Right, I mean, like, you know, like it's in a 6-dimensional space, which is already far above human comprehensibility. And then you're like, yeah, I'm computing gradients in 6 dimensions, and you're like, but, well, okay, but like we can look at the weights here. Yeah, that's a good idea. Let's kind of like look at the weights. So like, the biases don't really move, it would appear. Right, so, okay, let's let it solve from, this is the same training set. So we're going to let Atom solve from this state, and then we'll look at the weights. So it's like, you know, the biases, that's good enough. So the biases don't really move. This guy goes up really high. This guy goes down, down. So they're all down, this guy's up. Okay, so let's see if we manually do that, like what that will look like. So this one was like up 2.5, and then like down 0.5, down 2, down 0.5. Okay, let's all remember that. I'm not going to remember it. Okay, so this is up 2.5. What does that do? Like it scales everything crazily. Okay. And then I don't remember the rest of them. This was down 0.5, I think. What? Okay, so that like shears it. It was negative 0.5, I think. Whoa, it's like already solving it. How would you come up with this, you know? Okay, now this one I think was negative 2-ish. Okay, that's like another shear type thing. I mean, some of the problem is that like this is off the screen, so like it's hard to tell what's happening there. And then this I think was also like negative 0.5. Yeah, that doesn't quite, oh, negative 0.5. Wait. No, that doesn't look the same at all. Okay, resolve. Okay, reset and resolve. Okay, so that's what we had. 2.5, negative 0.5, negative 2, negative 1. 2.5, whoops. Negative 0.5, negative 2-ish, negative 0.5. Okay, yeah, I didn't, that's not, okay, let's just go to a different training set. Okay, so like, we're probably definitely going to have to do a flip over the horizontal, because this green guy has to get all the way down there. So let's just do that. Where's the horizontal flip? Yeah. Okay, horizontal flip over the horizontal axis. Good. Good. Then, although that kind of upset our blue guy. Should we like shear the blue guy over? Let's like shear the blue guy over and then do a horizontal flip. Right? Okay, how do you do a horizontal flip? It's this one. No, it's this one. Yeah. Okay, okay, okay. Right? And then, so now we need like the red guy. So like unshear it maybe? Like, is that still a horizontal shear? Yeah, like that. No. Oh. Like, oh no. Okay, that's not... I think, you know, like, we should interpret ourselves as a greedy, action agent. There's probably a better name for that. Where, right, like incrementing and decrementing each of the weights, each of the 6 weights, these are our available actions, right? So like at any state, we have 12 available actions. And so then what you can do is you can like guess and check, or like you can just try each action, and then like whichever action best increases our reward, our utility function, then like we go with that action. However, that's very tedious, so like I'm not sure I want to do all that. Also, it's kind of hard to eyeball. I could have a little, you know, like a little display saying like total error, but I'm not going to do that. So, anyway, we seem pretty stuck, right? Like we got green pretty good. Green's, oh yeah, that was another idea I had. So like if you try to fit, like just try to fit 2 of them. Yeah. We're just going to try to fit 2 of them, because I don't think that's that hard. If you fit 2 of them. So let's ignore the green guy and try to fit blue and red, because they're the closest and they're both kind of similar in like the direction and stuff. So let's see, I can either like move the entire thing over. Yeah, let's just move the entire thing over. Kind of like that. And then if I can just like introduce a little shear to get the red more lined up. No. Yeah. Oh no, that's... What's... Okay, that's shearing the blue more. Okay, so then what if I go vertical? Like... Oh yeah, no. Yeah, okay. What's like, yeah, that's kind of the thing. Like, if you can fit like one of the points, let's just fit the easiest point, which will be blue. So we're just gonna fit that point. So, whoops. I want to like shear like this, yeah. And then I think you compress horizontal. No. Maybe. Yeah. Wow. Well, I mean, it's like, there you go, we fit red. It seems to be like there should be a thing like if you want to fix one point, there should be like pairs of actions that like You know, like you should be able to move these guys, for instance, while keeping the red one fixed. Right? I mean, that's kind of what we're doing, I guess. Yeah, that kind of does that. Because, like, you can compensate. Is this even possible? I mean, like, does anybody... I'm not sure this is possible. Like, because, well, let's see what old gradient descent does. Uh-huh. Yeah. See, it's like maintaining the angle of all three lines whilst it's like scaling in that direction. Yeah, but anyway, is that really the best way to solve it? Like, cause the size of these weights, I mean 5.4, that's a huge weight. Can you solve it with a smaller weight? Oh, I guess not. Like, you have to do that crazy thing. I'm not sure this is human possible, you know? Okay, let's just try a different one. Oh, you know what we should try? We should try 2. We should just try weight sets of size, or training sets of size 2. That's what I'm gonna do. If I can find the training set situation. Where is it? Here it is. Training size 2. No, not 20. Yeah. Okay. 2. Like, it's always possible to do 2. Yeah. That's the thing, right? I mean, like, you want to move... You have to move this guy over whilst moving this guy in the opposite direction, right? This guy needs positive x displacement. This guy needs negative x displacement. Like, how do you do both simultaneously? You could always flip on the vertical axis, right? Yes. No. No, how do you... Yeah, that. Do I want to do this? Yeah. No. No. Because, you know, and then you can say, like, okay, this guy, and then, right? Okay, we fit red. We fitted the red thing, more or less. And, but I mean, like, the green still has a long way to go. Is there anything available that... No. Like... Because right? Okay. And, right? So then I just need to move it in that direction. Oh, I think you can just use biases if you just need to move it. Oh, that's pretty good. That's pretty good. That's pretty good, if I do say so myself. Oh, is that better or worse? I don't know. Right? That's pretty good. Okay, I'm gonna write those weights down. Wait, did I say that right? I'm gonna write the weights down. And then we're gonna compare with Atom Optimizer. Can I? Oh no! Oh, yeah, I forgot. I forgot it auto updates. Wow. Because I was pretty proud of myself, frankly. That's alright. Okay, so we'll do this one. I mean, it's like... I think I should flip it. That's apparently all I ever do, is I just like flip it on the horizontal axis. Right? Because that gets the red. Oh yeah, but that messes up green. Yeah, okay, so let's not flip it. It's like basically you need to rotate it. Well, yeah, you can rotate using flipping, can't you? So, I rotate this way. Good. And then I rotate the other way. Or I flip it the other way. Yes. Oh no, that didn't... Yeah, that... Okay, then I flip it again. We will unflip the earlier flip. Yeah, okay. Yeah, so we're definitely rotating it. Okay, so if I make this, spread that out, and then like, can I shear it? Like, get some shear action going? Yeah, okay, that's a lot of shear action. And then, no. Yeah. Wow, this is not going well. Right. Do that again. Okay, so like it's... Yeah. It's like it rotates everything. It also moves it. Okay, let's see if like we can figure out how to pull that motion off. Yeah, like basically make the thing into a diamond. Okay, so we're gonna try to make the thing into a diamond. So I'm gonna shrink it down a little. Right, we know how to do that. But now we wanna like make it into a diamond. How do you make it into a diamond? Yeah, kinda like that. Kinda like that. And then yeah, basically like that. Look at that, we just made a diamond. And then we want to like compress it more. Which one compresses? Compress, and then compress, and then compress. Whoa, we just made a diamond. That's amazing. That's amazing, look at that. Does that help me in any way? I mean, in terms of solving the thing? I mean, yeah, then you kind of have to like rotate it some more. I'm not, kind of like that. And then, yes. Wow, I'm kind of figuring out how to rotate. This is very cool. So, yeah, like rotate a little bit more. No, yeah. And then, whoa. Oh. Okay, and then it has to expand. No. Yes. Okay, I basically solved it. And then expand some more. Oh! Look at that. Did anybody see that? No. That's so sad. Whoops. But anyway, we solved that one. That's solved. Okay. Alright, let's do another one. Yeah, this one's like hard to see, but like this has to go over there. Yeah. That's not... Well, you know, like the last one we used Atom to kind of give us a hint on like the first move or something, so let's just do that. It's like a rotation. Okay. So it's basically just like a slight rotation and then, right. Okay. I could probably do that. I mean, yeah. I don't think I could do that. Okay, so it's compressed it like this. Okay, then we rotate like over this way. And then, kind of like that. And then, yeah, and then, okay. And then like this is kind of over. And then like kind of down. And kind of back over. And, kind of compress some more. And, yeah, I mean, like, that's kind of it. And then go up. That's kind of it. That's not what it got, but... Right. Close enough. I mean, you know, like, there's multiple solutions when you have two, right? Like, if you run the optimizer multiple times, it should find multiple... Well, maybe not, because we're starting from the same initial condition. But like if you just completely randomize the starting, maybe it'll be different. I don't know. Okay, now solve. Yeah, it did the same thing. Okay, that's fine, whatever. Okay, different training set. Okay, we have to move this one here, that one down. So... I think it's going to be like a counterclockwise rotation. It's going to be a lot of compression. Or I mean, this is what I call compression. I don't know if that's like... So, okay, so scale it down. Good. Then, we just need to rotate it a little bit. Just a little bit of a rotation. Kind of like that. And then... kind of like that. Move in it. Oh, yeah, that's okay. What if I put this down
and then like, yeah, just rotate it back the other way. Like that. No. Doing it like that goes over there. And then these go down. Yeah, no, that wasn't. What the heck is happening? Flip it. Right? And then like rotate again. That's close. That's close. Okay, let's see how the thing solves it. Okay, so we got like the diamond shape. And then, okay, and then like it shears it. I mean, the problem is that like it's updating all of these simultaneously. It's like, stop updating all the weights simultaneously, you know? Okay, let's do a different one. How long have I been going here? 30 minutes. Alright, I'll do one more. This is pretty fun stuff, guys. I don't, you know. Okay, so like a different training set, because I don't like that training set. Alright. Okay, so this one has to go like 1 unit. And then this guy has to go down in multiple units. So, yeah, how are we gonna solve that?
How are we gonna solve that?
Yeah. Okay, so I think it's like we're gonna have to have massive like vertical compression and horizontal compression, maybe. And kind of like that. Okay, and then a little rotation. Kind of like that. Maybe. And then like that. Right? That's already pretty close, because then you just bring it over. Yes, so, but like making it more better even. Do like, what am I looking for? This? Yeah. Oh, there it is. Boom. Solved it.
Solved it. So it seems like conceptually. Oh, let's see how the machine does it. Also, I saw a paper somewhere where it was like a transformer model can predict. I think like you feed it a training set, and it outputs the weights for like, I guess like a fixed architecture neural net that will convert, that like fits the input data.
Right, so it's like you don't even need gradient descent, you know. But so anyway, it seems like conceptually from like a human perspective in terms of solving training sets of size 2, I don't know, like you rotate it. That's what I was saying. Like you just rotate it. Okay, see how the machine solves it. Okay, so like it's doing like a weird shear in. Okay, then it kind of flips it over. Great. But that's kind of like what my solution looked like, I think. I don't know. Okay, I want to do one more to test my general hypothesis. Ooh. Wow. Yeah. What the heck? Oh my god, I don't know. Okay. So it does seem like if you like start off with by shrinking the grid, that always seems like a good thing. I don't know why. Right? So okay, so then like let's just move everything over. Right, okay. And see, but now the green has to travel less than the red. So if I could fix that, but let's move them up first. Okay, then I need to fix the red. Is there anything that will help me fix that? Well, yeah, just that. Yeah, compress everything onto a line. Yeah, solved. Yeah, because like the two, what is this, Y? They're on the same thing, so you compress all the grid points to a single line. And then problem solved. Okay, let's see what the machine does. Yeah, it didn't quite do the same thing, but I solved it. Okay, so yeah, this is going. Okay, so I'm gonna compress everything so it's here, in between the two target points, and then I'm gonna rotate. Easy. Okay, and then like get in between. Okay. And then well, I think if we flip on the vertical axis, right? You always want a good flip on the vertical axis. It's perfect. Okay. And we just need to expand. No. Actually, do that? Does that? That doesn't help, really. Kind of. But, yeah, I guess I was looking, well, okay, yeah, that wasn't, yeah, you're gonna need massive scaling here, because, okay, so we're gonna need to flip on the horizontal axis. How do you, oh, so like do this, and then, kind of like move it, like shear it more, okay, and then, okay, that's pretty close. Okay, let's see what the machine does. Whoops. It did it completely differently. Yeah, but what did it do? I mean, like, it's hard to tell what it's doing. Okay, so, like, it does, like, a diamond shape. Okay, then it completely, like, flips it. Right. So, like, the 0 is all the way out here. I'll do one more. Cause yeah, 40 minutes. I'll do one more. All right. Well, my instinct is to make everything small. Not sure that's a good instinct, but okay, and then yeah, I think we're gonna want a good flip on the axis type thing, or you could just keep it like that and then move it over, kind of, and then like that, and then move it over, and then like expand. Yeah, that's expanding the wrong way though. Move that down, then expand. Oops. Where's the expand one? Yeah, we're getting there. This is just gonna be a massive wait. Keep going. Yeah, man, that's totally fitted. Okay. So this is like human solution. Let's compare the machine solution. Right, so like we're separating everything out. Let's see what the old machine does. Oh, it solved it way better. Oh, it just like rotated it. Right. Listen, man, if you want to think like a neural net, you know, this is the type of stuff you have to do.